Imagine a story, not just any story, the grandest story of all. The story of everything. Every star, every planet, every person who has ever looked up at the night sky and wondered. Our best scientific understanding begins with a single, spectacular event. We call it the Big Bang, not an explosion in space like a firecracker. The explosion of space itself. The moment our observable universe burst from unimaginable density and heat. The ultimate origin story. The beginning of time. The beginning of space. The beginning of all the matter and energy we see today. It might sound fantastical, like a myth, but it's not a guess. It's a scientific theory, built on a mountain of evidence. A framework tested and refined for decades. Everything we know, from the farthest galaxy to the atoms in your own body, was once compressed into a space smaller than a single atom. Then in an instant it began to expand, and it's been expanding ever since. The starting point of our cosmic journey, the first page of the universe's autobiography. Every direction you look, every star you see was once right here with you, in that tiny, hot, dense state. The atoms in your hand were forged in the hearts of stars from primordial gas. We are, literally, the children of the Big Bang. This theory connects us to the very beginning of everything. It's a powerful idea that places us in a grand, unfolding cosmic narrative. Not just a story about stars, not just a story about galaxies, it's our story. So how did we piece this tale together? How do we know it's reality, not just a beautiful idea? Science is a detective story. We look for clues left at the scene of the crime. The crime scene is the entire universe. The event happened 13.8 billion years ago. Clue: light from distant galaxies. Clue: a faint glow that fills all space. Clue: the elements encoded in our world. We had to learn how to read them. Our journey into the cosmos is a journey into the past. In the 1920s, an astronomer named Edwin Hubble made a revolutionary discovery. He was observing distant galaxies, those great islands of stars far beyond our own Milky Way. He noticed something strange about their light. The light from nearly all of them was stretched out, shifted toward the red end of the spectrum. This phenomenon is called redshift. It's similar to how the siren of an ambulance sounds lower in pitch as it moves away from you. For light, moving away stretches its waves, making it appear redder. Hubble had found that the universe was not static. It was getting bigger. Hubble didn't just find that galaxies were moving away. He found a stunningly simple relationship, now known as Hubble's law. The farther away a galaxy is, the faster it's moving away from us. This wasn't a random scattering of galaxies. It was an ordered, uniform expansion of space itself. Imagine baking a loaf of raisin bread. As the dough rises, every raisin moves away from every other raisin. A raisin twice as far away will appear to move away twice as fast. The galaxies are the raisins. The fabric of space-time is the dough. We are just one of those raisins, watching the others recede. This discovery was the first observational pillar of the Big Bang theory. If the universe is expanding today, then it must have been smaller yesterday, and the day before that, and the day before that. If you run the clock backward, all the galaxies rush back together. You can rewind the cosmic movie, watching everything in the universe converge toward a single point in the distant past. This expansion is the dynamic engine of our cosmos, the ongoing process that started with the Big Bang. It's the motion that defines the entire history of the universe. It's important to understand that the galaxies themselves aren't flying through space. Space itself is expanding, carrying the galaxies along with it. This is a key concept. There is no center to this expansion, no single point from which everything is moving away. From the perspective of any galaxy, all other galaxies are moving away. Every point can be considered the center. This is a humbling realization. It removes us from any special, privileged position in the cosmos. We are simply part of a vast, dynamic, and ever-growing universe. Let's, travel back in time to the very first moments of the universe. What was it like? Well, the word extreme doesn't even begin to cover it. At 1 second after the Big Bang, the universe was a seething inferno, billions of degrees hot. It was a dense soup of fundamental particles, quarks, electrons, photons, neutrinos, all zipping around and colliding with incredible energy. There were no atoms yet. There were not even protons and neutrons. The universe was just too hot and too dense for them to hold together. It was a truly primordial state of matter. As the universe expanded, it cooled. And as it cooled, things began to change. Within the first few minutes, the temperature dropped enough for quarks to bind together, forming the protons and neutrons that make up the nuclei of atoms today. Then for a brief period, conditions were just right for these protons and neutrons to fuse. This was the era of Big Bang nucleosynthesis, the universe's first foray into chemistry. It was during this time that all the primordial hydrogen and helium in the cosmos were created. The universe was, writing its first elemental recipe. After about 380,000 years, the universe cooled further to a few thousand degrees, about the temperature of the surface of a star. This was a critical threshold. Electrons were finally able to combine with nuclei to form the first stable, neutral atoms. It was the moment the universe became transparent. The light that had been trapped within the hot plasma was now free to travel across the cosmos, unimpeded. This is the very light that we now detect as the cosmic microwave background. It is a direct message from that transformative era. From there, the story of the universe became one of gravity. Over millions of years, tiny variations in the density of the primordial gas began to grow. Regions that were slightly denser had slightly more gravity, and they pulled in more material. Gravity is relentless. These dense regions became the seeds of cosmic structure. They grew into vast clouds of gas, which then collapsed to form the first stars and galaxies. The dark, transparent universe slowly began to light up as the first stars ignited, ending the cosmic dark ages and beginning the universe we see today. We have this incredible story, a detailed history of the universe going back 13.8 billion years. But there's a limit. There's a wall. Our understanding, based on our current laws of physics, hits a barrier at the very instant of the Big Bang. Our equations, the powerful tools of Einstein's general relativity that describe gravity and the expansion of space, break down. At time zero, the theory predicts a point of infinite density and infinite temperature. This is what physicists call a singularity. It's a point where the math no longer works. A singularity isn't a physical object, it's a sign that our theory is incomplete. It's like trying to divide by zero. The answer is undefined. General relativity is a brilliant theory for describing the large-scale universe, but it doesn't include the physics of the very small, the world of quantum mechanics. To understand the origin of the universe, we need a theory that can unite these two great pillars of modern physics, a theory of quantum gravity. We don't have one yet, and without it, the moment of creation itself remains shrouded in mystery. This barrier exists at what's known as the Planck time, an infinitesimally small fraction of a second after the Big Bang, about 10 to the minus 43 seconds. Before this moment, the universe was so small and so dense that quantum effects would have dominated the nature of gravity and space-time itself. To describe this era, we need that missing theory. It's the holy grail of modern physics. Until we find it, asking what happened at the moment of the Big Bang is like asking what's north of the North Pole. The concept breaks down within our current framework. So when we talk about what came before the Big Bang, we are stepping outside the realm of established science. The very concept of before is problematic because time and space, as we know them, began with the Big Bang. If time itself started then, asking what came before is a meaningless question. It's like asking a movie what happened before the first frame. But our curiosity doesn't stop there. Scientists are explorers, and even when we can't see over the wall, we can't help but wonder what's on the other side. So, what could have been there? What could have preceded our universe? Scientists, being relentlessly curious, have some ideas. These are not established theories, speculative possibilities on the frontiers of cosmology. One idea: our universe emerged from a pre-existing state. Maybe the Big Bang wasn't the beginning of everything, just the start of our current phase. The singularity might not be infinite density, but an extreme, finite state we don't yet understand. One popular model: cyclical universe. The Big Bang isn't one time, it's an endless cycle of expansion and contraction. Our universe expands, then gravity could pull everything back in a big crunch. That collapse leads to another hot, dense state, then a rebound into another Big Bang, creating a new universe. Call it the bouncing universe. It avoids a singular beginning by suggesting an eternal series of cycles. Another mind-bending idea: string theory and advanced concepts, the multiverse. This is the idea of the multiverse. Perhaps our Big Bang was one of many. Our universe, a single bubble in a vast, foaming sea of universes, each with its own Big Bang, maybe even different laws of physics. Some versions: universes collide, collisions can trigger Big Bangs. Our beginning might be an event in a larger, higher-dimensional space. These ideas are thrilling, but they are speculation, mathematical possibilities from pushing beyond Einstein. We currently have no way to test a bouncing universe or a multiverse. They are tantalizing glimpses, driven by the desire to answer the ultimate question. Even at the edge of knowledge, imagination guided by math and logic explores. The quest for answers is as boundless as the cosmos itself. Our journey to understand the universe's origins has revealed not just what we know, but also the vastness of what we don't. As we mapped the cosmos, we stumbled upon some profound mysteries. We discovered that the stuff we're made of, the atoms that form stars, planets, and people, is just a tiny fraction of what's out there. About 27% of the universe seems to be made of something we call dark matter. We can't see it. It doesn't emit or reflect light, but we know it's there because we can see its gravitational effects on the galaxies and stars we can see. We can watch galaxies spinning so fast that they should fly apart, but they don't. Something extra, some invisible mass, is holding them together with its gravity. That something is dark matter. We don't know what it is. It could be a new kind of subatomic particle that we haven't discovered yet. Scientists around the world are running sensitive experiments deep underground, trying to catch a fleeting glimpse of one of these particles as it passes through the Earth. Finding it would be a revolution in physics, but for now, it remains one of the biggest question marks in our cosmic inventory. And the mystery gets even deeper. In the late 1990s, astronomers made a shocking discovery. They expected that the expansion of the universe might be slowing down due to the pull of gravity. Instead, they found the opposite. The expansion is accelerating. Something is pushing space apart, working against gravity. We call this mysterious force dark energy. It makes up about 68% of the universe. It's the dominant component of the cosmos, and we have almost no idea what it is. It's a cosmic anti-gravity that is shaping the ultimate fate of our universe. So, when we look at the universe, we realize that we only understand about 5% of it. The remaining 95% is dark matter and dark energy. These are not small details. They are the main characters in the cosmic story, and we've only just been introduced. Understanding the nature of dark matter and dark energy is essential to building a complete picture of the cosmos, from its beginning to its ultimate end. These great unknowns are a humbling reminder that our exploration of the universe has only just begun. The map of the cosmos is still mostly blank. The question of what existed before the Big Bang remains the ultimate cosmic mystery. It lies at the very edge of our scientific understanding, a place where our most powerful theories break down and the familiar concepts of time and space may no longer apply. We have ideas, the bounce, the multiverse, the birth from nothingness, but these are signposts pointing into an undiscovered country. They are not yet science, but the fertile ground from which future science may grow. The truth is, we don't know. And in science, we don't know is a powerful and exciting phrase. It's an invitation to be curious, an invitation to keep asking questions, to keep building better telescopes, to keep devising new experiments, to keep dreaming up new ideas. Every great discovery in the history of science began with someone who was not afraid to say I don't know, and then followed it up with, let's find out. The quest to understand our origins is one of the most fundamental drivers of human civilization. It connects us to our ancestors who looked at the same stars and wondered, and it will connect us to our descendants who will carry the search forward. The universe is under no obligation to make sense to us. It is vast, ancient, and filled with wonders beyond our current comprehension. But the human mind has a remarkable capacity for understanding. Piece by piece, clue by clue, we have constructed a story of the cosmos that is far grander and more astonishing than any myth or legend.